Right. So we are the team from Metro State University here in Denver. For the past 2 months or so, our cohort has been centered around the research question, what are the environmental impacts of the 2020 Grizzly Creek fire? And how are they felt by the people and communities along the Colorado River in Garfield County? All 4 of us interns have different specialties within the greater umbrella field of earth science. And researching a specific wildfire gave each of us an opportunity to investigate data that corresponded to our interests. Using the parameters listed, we found data that helped us understand the fire's impact on ecological communities, vegetation, water quality, as well as examining the incidence of debris flows in the wake of the fire. We used these data sets in conjunction with information from 2020 census and community reports to better understand how the city of Glenwood Springs and the greater Garfield County is vulnerable to wildfire. This was an opportunity for all of us, first and foremost, to explore how to access and present this kind of data. Speaking of us, the interns this year are myself, Tesia Mancosky, a student in geology, Ha Mu, a student in environmental science, Rachel Sadler, student studying GIS, and Riley Sundberg, studying biology and GIS. We were joined by our advanced interns, Rosie Patrick and Meghan Smedes, as well as our awesome faculty advisors, Dr. Sylvia Brady and Dr. David Parr. We want to acknowledge that we are speaking today about the traditional homelands of the Uncompahgre Ute Nation, who were removed from their land in 1868 and never compensated in any way for the cession of over 4 million acres to the US government. We want to additionally acknowledge that Metro State stands on the stolen land that was of great spiritual and economic importance to many Native nations and exists today only after displacing the entire working class community of our area that was forced out of their homes by eminent domain in the 1970s. Again, one of our goals as a cohort was to build a project that afforded each intern an opportunity to work within their specialty. As we brainstormed potential directions, it became clear that looking at a wildfire event gave us ample space to ask individual questions pertaining to biology, environmental science, GIS, and geology. More generally, we wanted to explore the topic of wildfire as it is a threat that is never far from our minds as residents of Colorado and of the greater Intermountain West. Fire has always been an integral part of Colorado landscapes and ecosystems, but the exacerbation of human-caused climate change and tremendous population growth in high-risk areas has transformed this once natural process into a major environmental and economic hazard in the last few decades. Climate change has created warmer, drier conditions, leading to longer and more active fire systems. The American Southwest is currently in the throes of a mega drought, the region's driest in 1,200 years. Lack of moisture and rising temperatures have led to increased evaporation, drying out soils and killing vegetation, increasing fuel availability. Studies indicate that human-caused climate change has doubled the number of large fires in the United States in the last 30 years. Today, more than half of Colorado's population, over 1 million people, live in areas at moderate to very high risk of fire. At the time of this presentation today, 4 wildfires are burning along the Front Range within 50 miles of all of our homes in the Denver area. So for this presentation, we looked specifically at the Grizzly Creek fire that sparked during one of Colorado's driest summers on record. And it was the biggest wildfire to ever burn in the White River National Forest. It was reported first on August 10th, 2020, in Glenwood Canyon, 1 mile east of the city of Glenwood Springs. Sparking in the median of Interstate 70, the fire quickly spread up both sides of the canyon and east towards the town of Gypsum, Colorado. It burned strongest from August 12th to August 19th and was 60% contained by August 26th. Total containment was not achieved until months later on December 18th, 2020. The main reason this fire burned for so long was that it was virtually impossible to fight the fire from the ground in the narrow and steep Glenwood Canyon. In total, approximately 33,000 acres burned. Fire marshals were able to determine that the cause of the fire was dragging chains on the highway, which sparked and quickly ignited the dried out vegetation in Glenwood Canyon. While there are no human casualties and no homes were lost, this fire resulted in the evacuation of several communities, closed I-70 through Glenwood Canyon in both directions for an unprecedented 13-day period, interrupted service at the Shoshone Hydroelectric Power Plant, blocked the Union Pacific Railroad freight line, closed all activity on the Colorado River and also in White River National Forest. Economically, the Grizzly Creek fire cost the state about $34 million to fight. The mayor of Glenwood estimated that the 2-week closure of I-70 resulted in tens of millions of dollars of loss to the local economy, dependent on tourism from the major transportation corridor, a loss that was felt even harder in a season dampened by the onset of the COVID-19 pandemic. The environmental impacts of wildfire are myriad and impossible to list exhaustively here. But within the burned area of the Grizzly Creek fire, entire ecosystems were changed, disrupted, or destroyed. Removal of vegetation during the burn increased sediment loading in the Colorado River, impacting plant and fish populations. The loss of vegetation and changing of the soil resulted in debris flows, particularly in the year following the fire. Burn scars additionally have an increased risk for flooding. Water quality degradation via burned material washing into the river impacted aquatic ecosystems and water quality for human consumption. This presentation will focus mainly on those first 4 topics. We will discuss habitat changes, vegetation loss, incidents of landslides, and the fire's impact on water quality in the Colorado River.
So to do this, here are our data sources we used to analyze the impacts of the Grizzly Creek fire. We used many satellites, such as Sentinel-1 and 2, MODIS, and Landsat 8 and 9. We also used data from the CDC, NASA, NOAA, and the USGS. All of our data is open source. Data can be hard to come by depending on the type and location. We ran into some of this, and I know other teams had similar experiences. So we are very grateful to these agencies for their publicly available data. Now, data is just as important as the tools used in creating this project. Most of our coding was created with Python. Specifically, we used a lot of pandas and geopandas for analysis and plotting. We used GitHub for open and reproducible science. In GitHub, we used Jupyter Notebooks as well as Google Colab for our code spaces. We used Google Earth Engine for some advanced plotting, and we used a little bit of ArcGIS Pro for some initial analysis. We intend on having this project available on GitHub shortly so that others can access our work. Part of what made our project successful was having access to open and reproducible science from others, and we want to contribute to that. To jump into our research and analysis, I will pass it on to Riley to discuss our area of study and its ecology.
And it is at this point that I'd like to acknowledge the land and all the beings living within them for the connections they build, the wisdom they inspire. Can you not hear me?
I can
Hello?
hear you, Riley.
Oh, okay. Cool. For holding us in the grand age for the land and the vast diversity of lessons from the others. The land misses the descending people and how it used to be treated. We have much to learn from the land and from these communities and to give power as we find our ways, new ways forward. I imagine the land also misses fires from the grasslands and shrubland to the montane forests that evolved alongside it, with the frequent low-intensity fires, and even the subalpine with its cooler climate and Douglas Fors has a history with fire. Next slide. Fires can create mosaics of habitat and can renew systems, create an open and mature woodlands, patchy young dense stands, and new open meadows, giving birth to a dynamic equilibrium, not of climax communities, a final stage of successionary growth, but shifting stages of succession, which in the broader landscape remain in equilibrium. Many communities and beings within depend on this dynamic shift in certain places. The threatened pinon jays, for example, need early successional pinon trees to cache food and mid-aged trees for the best forage. Lodgepole pine need fire to activate their seeds, and the newly open canopies is perfect for their new saplings. In the White River National Forest, where this study takes place, all of the above communities exist as well as many others. Next slide. With the intense and more frequent fires from fire suppression and climate change, the balance is in danger. And in relation to the land by dominant culture has changed things. Habitat degradation and loss due to mining, energy development, modern agriculture and ranching, recreation, invasive species, and so on. All of these have reduced the dynamic equilibrium's potential. Represented on these graphs from the state of Colorado's biodiversity, hundreds of threatened species are poorly protected and at risk from continued habitat degradation. Each of the habitats shown here present the various communities found in Colorado. Each community contains dozens of plants, birds, mammals, reptiles, and amphibians at risk, and many are without sufficiently protected habitat, as represented by the red and orange. Some notable callouts for this research of over half poor and fair protection are the pinyon junipers, the mixed mountain shrub, the sagebrush, aspen, and ponderosa pine. Of note, not mentioned here, cottonwood forests are threatened in part by the flood prevention, damming, and ahistoric flood regimes, which limit the sapling's growth. Within the black circle on the bottom right there is Garfield County, which has a large percentage of poor long-term community protections, including where this fire occurred. Next slide. Nearest the Grizzly Creek fire, Glenwood Springs receives connection, experience, slope stability, and water filtration from these ecosystems. Hanging Lake, the trails, the activities, and the many hot springs draw people from afar. They help heal the minds, bodies, and spirits and bring wealth to the human community there. Many of these gifts and the gift of life are dependent on the health of the non-human beings whom are dependent on this vegetation. Looking at which of the vegetation nation was lost, here is Parr.
This is a burn severity map of the Grizzly Creek fire. Within the fire boundary, the dark red indicates a stronger burn severity, and the light red to light blue areas indicate lower burn severity. The Colorado River and the I-70 also run through the burn area. Next slide, please. Immediately after the fire, a rapid assessment of vegetation condition after wildfire, RAVG, was conducted. RAVG is a mapping program that creates standard map and reports about the condition of plants and trees after a wildfire. The vegetation at the site was categorized into 6 groups. In the assessment of vegetative loss, it was found that grasslands, shrublands, non-vegetated areas, evergreen closed tree canopy, and mixed evergreen deciduous open tree canopy vegetation groups had the most loss by acres. Next slide, please. This graph shows the basal area loss by percentage of each vegetation group. Basal area loss is derived from basal area. Basal area is the measuring of the width of a tree trunk, including the bark, 4.5 feet above the ground. It helps determine forest stand density, forest regeneration needs, and wildlife habitat requirements. It is also done for economic purposes like determining timber density for its monetary value. Basal area loss is the percent change in basal area relative to the pre-fire condition. It provides data on what vegetation is present in comparison to what was there before the fire. Basal area loss is categorized into 4 quarters that ranges from 0 to 100%. Within each vegetation group, the loss percentage is greater in the 0 to 25% and 75 to 100% range. 0 to 25% basal area loss means there was a slight fire damage to the vegetation, and 75 to 100% basal area loss means the mortality of the entire vegetation. These ranges are consistent with the fact that this was an intense, fast-burning, and fast-spreading fire. Next slide, please. To have a better visual of what the vegetative loss looks like, I downloaded images from Landsat through NASA Worldview with a lot of help from Dr. Elsa Culler. The image on the left is a satellite image of the burned area in July of 2021, 1 year after the fire. As you can see, the burn area is still very prominent with very little green. The image on the right is a satellite image of the burn area in July of 2022, 2 years after the fire. It shows a lot more vegetative regrowth indicated by the green areas. And now Riley will touch more on the vegetative regrowth in the area.
To measure the regrowth, we used the NDVI, the Normalized Difference Vegetation Index, as was taught in one of the courses here. The method uses NIR, which is near infrared, and red detectors collected by various satellites to determine vegetation presence and relative health. This cannot detect what is growing per se, but can detect if something is growing, or if compared to known similar vegetation and or the same area over time, can indicate a change in health. And why not green light, you might ask? Well, because NIR and red bands of light can detect stress earlier than just green or visibly can. And it uses an index, typically from -1, which is represented as red, showing the less vegetation or a negative change, while 1 and green represents vegetation or a positive change. And in the next slide, I talk a little bit more about how we calculate NDVI and downloaded and configured the data that we needed. We use the Piers API application from NASA Earth Data with assistance from C of Boulder's EarthPy library and the team there, as exampled in the upper right code there. For more detailed resolution, I wanted to bring in the harmonized Landsat and Sentinel-2 data. This is a product from the EU and US satellite cooperation, and it provides a closer resolution of 30 meters by 30 meters every 2 to 3 days in theory. More on that. It's a little more unwieldy than the MODIS. The bands have to be downloaded individually and NDVI calculated manually. In addition, some dates had missing data, which muddied the analysis. So certain dates had to be selected that were both complete and without clouds. And Dr. Elsa Cooler helped me a lot with that. As seen on the bottom right there, you can see the big chunk of no data and the one with the little clouds. The MODIS product was used for some graphs. It's easier. The NDVI is pre-calculated, it's pre-cleaned, but the resolution is only 250 meters every 16 days. Now let's look at some of the results of the HLS. Here is the comparison of regrowth side by side of 3 years of NDVI data compared to the prior year. In the first image, the patchy loss of vegetation can be observed. Certain areas, the darker red indicating greater loss, the strip in the bottom right being the Colorado River and the highway, likely where the cottonwoods would be growing. In the following 2 years, a steady positive or green can be observed. This indicates that a type of vegetation is improving over those 2 years. But on an index of -1 to 1, it can make it difficult to see if there are issues in certain areas. So in the next slide, I changed the index from -0.1 to 0.1. By doing so, you can see several areas with consistent issues of regrowth. Later, this will correlate with landslides, but the rest of the area appears to be regrowing nicely, while those circled areas suggest that the areas may have been burned particularly hot and may require some assistance such as mulching or other stabilizing methods to ensure regrowth. Next, I wanted to pair this with some weather data. So I pulled in, on this next slide, some of that NOAA's NCEI, which utilizes 90,000 weather stations, mostly precipitation, but also some other data. This was located using the Climate Data Online daily summaries and searching for weather stations that had desired data near the fire. Mostly I used the one on the bottom there, that is a Glenwood Springs weather station. And there are some of the code that we used to bring it in. Next slide. So here, the precipitation data is from 2017 to 2023 and summed yearly to compare with the changing NDVI. The graph is from MODIS and compares the change within and just outside of the fire. The sudden drop in 21 is the year after the fire. And by the end of 2023, the NDVI has returned to about half its index, showing good progress, but the composition is unknown from this data. And recovery can take 7 to 10 plus years to reach a similar community composition as before the fire. Local stewards there are working to limit the invasion of invasive plants to aid that transition. And you can see on the bottom graph there that heavy rains likely helped the regrowth in areas that still had roots and soil. But these heavy rains had other effects, which Tesia will explore more here in this next slide.
So within the discussion of the impact of wildfire on vegetation in the area, it is really important to note how much healthy vegetation and soil is important for the mitigation of other geologic and environmental hazards. Vegetation serves any number of roles in an ecosystem, but it also plays an important role in the hydrogeologic system. Plant and tree roots are responsible for keeping soil in place on steep slopes. Where there is great loss of vegetation, there is also great instability of soil, as the top layer of material loses its anchor to the hillside. Erosion is intensified as the soil has nothing to hold it in place during precipitation events. Additionally, hot burning and long-lasting fires can result in the formation of hydrophobic soils. This happens when gases from the combustion of plant material penetrate the soil and condense into a waxy coating as the soil cools. This coating coats all soil particles and aggregates and forms a distinct layer that appears on top of the soil surface. These water-repellent soils create overland flow scenarios that increase the risk of flooding, as well as deter vegetative recovery because the water cannot penetrate the soil profile. Unstable slopes and hydrophobic soils both increase the likelihood of debris flows after wildfire, which Rachel will talk more about now.
Like Tesia said, these steep burn slopes are at a high risk for landslides and debris flow. Now, a landslide is the movement of mass of rock, debris, or earth down a slope. And a debris flow is a type of landslide where water is added into the mix and it creates a slurry that flows down. These are extremely dangerous because they can take many lives and cause significant damage to the surrounding land. In the case of the Grizzly Creek fire, like you see in this picture here on the right, a debris flow will run down the mountainside, across I-70 and into the Colorado River. This picture here is after debris flow in late June of 2021. Now, this was just one of 26 debris flows along I-70 and 8 that happened in the Grizzly Creek watershed during that year. In 2022, the National Weather Service issued a flash flood warning of the burn scar area because of large rainstorms that resulted in life-threatening flash floods and debris flows. Many events like these in the years post-fire closed I-70 for days until the area was safe for travelers again. These hazards also significantly impact the water quality of the area and downstream. This can be seen by an increase in turbidity or the cloudiness of the water. Over a year or two, the soil will become less hydrophobic and vegetation begins to grow back. However, during this time, we still do see debris flows and landslides occur. So we wanted to map these hazards of the burn scar area after the fire. Next slide. To do this, we used synthetic aperture radar, or SAR, to show a change in the landscape. SAR data is collected by Sentinel-1 satellites from the European Space Agency. The data is collected from a sensor on the satellite that sends energy waves down to the surface and records the amount of energy that is reflected back. These satellites are able to collect data both day and night, and during any type of weather. With precipitation events, we are more likely to see landslides and debris flow because of the loose hydrophobic soil. SAR is great at detecting these because it can see through the cloud cover and can still collect data during these events. This map you see here on the right is just after the rainstorm and debris flow you saw on the last slide. The black line is our fire boundary, and red spots indicate a change or movement of the surface, and blue represents land that has not changed or moved. So we can see here where there were some possible landslides. We would have to confirm these with either a field assessment or using satellite images, but SAR gives us a great way to initially determine where landslides might have occurred. In this map, there are some large spots along the left side of the burn scar and a few below I-70, which is our yellow line in there. And these are near steep slopes that lead right into the Colorado River and some smaller rivers around. I was able to produce this map with some code, some open and reproducible code from Nassim Mosafari Amiri and Elsa Kohler. In this code here, you see we are creating start and end dates based on our time range of interest. So for this one here, it was just before and after that debris flow. Then an image collection was created and filtered based on SAR images available from Sentinel-1 during this time frame. A timestamp list was created to show all dates where the images were available. Then the difference in the images were calculated and mapped with Google Earth Engine to create the map you see here. And it's cool to see where there were changes after a rainstorm, but we were also curious about landslides during each year. Now, this data can be impacted by reflection of snow. So we decided to look at summer months during the growing season. In Colorado, especially in the mountains, we still receive snow through May. So our data was collected from the very end of May to the end of September. This 2020 map on the left here shows a lot of burning still and change on the east side. These could be landslides, but this could also still be from the fire because it burned until December of that year. The 2021 image is a bit more telling. This zoomed in part here, we can see lots of landslides happening on the west side of our fire boundary. We still do see some by I-70, but most are along this west slope. And as years pass and soil starts to recover, vegetation can begin growing back. So how does that connect with landslides we see from our SAR data? In this next slide, we are trying to see if there's a connection between landslides and areas that haven't had vegetation recovery. We have the NDVI here on the left that Riley showed earlier, and the SAR on the right. Both are from 2022 to 2023. We can see some similarities in the yellow circles in the left, top, and right. These are spots that are not growing back yet. And it also aligns with where there are landslides or movement of the soil happening. So these landslides could have been a possible reason that was making it harder for vegetation to regrow. One spot that doesn't quite connect is in this black circle in the middle of each map. We see some land movement from the SAR close to the edges of the black circle, but the NDVI is bright pink in the middle. Now this could just be a region where the burn was particularly severe, and it could benefit from some additional remediation steps that Riley mentioned earlier. Landslides and debris flow are just one part of a network of events in the changing ecosystem after a wildfire. They can be caused by precipitation events and also affect how vegetation regrows. Landslides, and debris flow especially, are two things out of many that change the water quality, which Tesia will be going into more detail about next.
So the Grizzly Creek fire burned along the Colorado River and through the White River National Forest. Glenwood Springs water supply is fed by Grizzly Creek and No Name Creek, both of which run through the fire's burn area. I was curious to look at how the fire impacted the surface water quality and examine what Glenwood Springs did to protect their water supply. When we are discussing water quality, there are any number of parameters to consider, depending on what you're hoping to monitor. Temperature, pH, salts, dissolved solids, suspended solids, and heavy metal concentrations, to name a few, can help tell the story. Fires can significantly impact water quality by increasing sedimentation and nutrient runoff into water bodies. The loss of vegetation from fires can lead to soil erosion, causing an influx of ash, debris, and chemicals that degrade water quality. Additionally, fire can release harmful pollutants like heavy metals and organic compounds, which contaminate drinking water sources. The impact of wildfire is seen most significantly in the year following the burn. Total suspended solids, which are particles not soluble in water, like sediment or organic matter and debris, peak immediately following the fire during major precipitation events, but continue to be a problem for municipal water supply for years after the fire. Heavy metal concentrations often peak in the water supply a year or two after the burn as they slowly leach from the torched soils. The data we used to look at water quality was pulled from two different USGS monitoring stations along the Colorado River. one located within the burn scar above Glenwood Springs and one downstream of the fire below Glenwood Springs. We did run into several issues with availability of data, but we were able to use the specific conductance of water to create an analog for total suspended solids and turbidity. Specific conductance is an indirect measure of the concentration of dissolved solids, which can then be correlated to suspended solids. We pulled the specific conductance data, multiplied it by a constant of 0.65 to get our TDS values. We care about suspended solids and turbidity because water treatment facilities are designed to handle specific sediment loads and can be rendered ineffective if the water has too much sediment. The Colorado Water Conservation Board estimates that the Grizzly Creek fire will continue to impact sediment loading in the Colorado River and turbidity during spring runoff events for at least another few years. So this graph here shows the trend of total dissolved solids at the monitoring station within the burn scar, with a little snippet of the code we use to call this data. In this 9-year plot, we can see that there are yearly peaks in TDS concentration during the spring melt and summer monsoon season, with the highest in this period in the months immediately following the fire. Total suspended solid concentration follows a similar pattern, and turbidity in the Colorado River spiked in the summer of 2021 when a 500-year monsoon rain hit Glenwood Canyon. Sensors within the no-name watershed measured a turbidity of 8,000 turbidity units during July of 2021. For reference, drinking water has a maximum limit of 1 turbidity unit. The water quality data is also consistent with both what Riley and Rachel were able to map with weather and precipitation data. The greatest incidence of mass movement in the year following the fire was found in the western boundary of the burn scar in the No-Name Creek watershed, where turbidity measurements were the highest. Prior to the burn, this was a pristine water source for Glenwood Springs. The incidence of the Grizzly Creek fire necessitated improvements to Glenwood's water infrastructure to protect their water supply. So the city of Glenwood was pretty quick to respond to protect the water supply, both during and after the fire. While it was burning, they shut off their intake from Grizzly Creek and No Name Creek, diverting instead to the Roaring Fork River, which flows into the Colorado River near Glenwood. Following the fire, they secured state and federal emergency funding to better protect the intakes in the burn scar, as well as upgrade their facilities to handle the increased sediment load during runoff and heavy precipitation events. Much of these improvements were done on an expedited, expensive schedule to beat the 2021 rain season. The town of Silt, which is about 21 miles west of Glenwood, has also experienced significant sedimentation issues due to highly turbid waters in the wake of the fire. Water filters that typically last years were overwhelmed in a year, costing the city of Silt over $100,000 to replace each year. Disparities in response to the fire throughout Glenwood County inspired us to look a little bit more at the census data. And Rachel's going to talk a bit more about how the local communities experienced the fire.
So we wanted to know who would be most impacted during this event. We got some data from the CDC and the Agency for Toxic Substances and Disease Registry. These two groups together created a Social Vulnerability Index, or SVI, and it's based off of census data. Social vulnerability refers to the demographic and socioeconomic factors that adversely affect communities that encounter hazards and other community-level stressors. The SVI is based off of 4 main themes: socioeconomic, household composition and disability, minority status and language, and housing and transportation. We have some examples here of specific factors collected through the census. The numbers in bold represent values for Garfield County, which is where the fire occurred. Almost a quarter of the population is below 150% of the poverty line, and almost a third of the population is Hispanic or Latino, and just below half the population is at an age where they might be dependent on others for help. We wanted to give some examples because these communities could be more vulnerable during natural disasters. This could be because of individuals being unable to relocate or living with a disability that prevents them from relocating. People might not be receiving all emergency broadcasts due to living situation or broadcasts not being sent accurately in multiple languages. Not having access to all the information necessary or the means to keep yourself and your family safe during these natural disasters can be extremely stressful. It makes it so important to have an evacuation plans that are easy to find, available in all languages, and have safety measures that represent a diverse population. So on our next slide, we see that we have a social vulnerability index. It takes about 30 different factors and creates a weighted scale to help visualize who is potentially more vulnerable during human-caused and natural disasters. It is shown as a relative index from 0 to 4. On our right here, we have some code pulling in our data, selecting Garfield County from Colorado, and plotting the SVI based on a final total index. This map, we have the fire boundary in blue here, with each colored area with a border is a census tract. In Garfield County, one census tract has 0 vulnerability. This is where Glenwood Springs is. It is the largest economic center of the county due to the tourist attraction of the hot springs. But we also see one census tract that has a vulnerability index value of 4. This is our bright red spot in the center there. This includes the town of Rifle. It is one of the largest regional centers for cattle ranching. Other areas within this county kind of vary in our index from a range of 1 to 3. So Garfield County has a very diverse population that would have been affected in various ways due to the fire that resulted in I-70 closing, disruptions of the Union Pacific Railroad, and the Shoshone Hydroelectric Power Plant. To take a closer look at how Garfield County was affected, I'll pass it over to Riley to discuss the after-fire recovery.
So I wasn't able to find too much on how Garfield itself was affected, but Glenwood Springs seemed like it was one of the most affected ones, being the closest to the fire, and their water infrastructure held up quite well and the trails opened up relatively quickly, both in the following year. This was in part because of how it was mentioned Glenwood Springs is quite a wealthy city. For all those reasons discussed, in 2019, they had the $19 million in sales tax and energy money from the west of Garfield County. 3.8 million was invested in the water infrastructure in the time after the fire, and it was the nation's focus because they had that political capital. And to close it up, we'll pass it off to Tish.
So I know we kind of threw a lot of data at y'all, but we did all kind of come to this project with a different background and interest. And it was really rewarding for all of us to see these paths converge to tell a more unified story of the Grizzly Creek fire using Earth data science. Though nearly 33,000 acres of White River National Forest burned, this research demonstrates that there is promising regrowth in the burn scar. Mapping the NDVI adjacent to the SAR data showed a relationship between debris flows in areas within the burn scar with low recovery rates. The greatest changes in water quality in the Colorado River were in the year immediately following the fire, similar to the incidence of landslides and debris flows. If we had more time, we would have loved to examine the relationship between spikes in water quality, incidence of debris flows, and major precipitation events. Our analysis of the census data showed that while Glenwood Springs was the closest city to the fire, they were also the least socially vulnerable part of Garfield County. That being said, much of Garfield County is at high risk for wildfire, and there are areas that are certainly less financially prepared to bear the burden of a major burn. You know, while we were able to tell a story of the impacts of the wildfire on the environment, there were certainly some speed bumps and roadblocks along the way. Data availability was a problem for all of us, and in some cases, we discovered that what we were looking for simply did not exist. There were cases of insufficient data for water quality questions, particularly when it came to heavy metal concentrations. The data, while freely available, was certainly not free to collect, and the high cost of regular water quality analysis is certainly a factor. Our examination of vegetation and regrowth does not tell the complete story of what has grown back, just that something has. The census data we used cannot tell us a complete demographic story either, as there are many of those who either do not complete the census or are not accurately represented by options on census forms. As a team, we do feel like we only just began to tell the story of the Grizzly Creek fire. If we had more time and unlimited funding, we're very idealistic, we would each continue to take this project further or in more directions. As a geologist, I would love to look more into the evolution of the soils in the burn scar, tracking how they evolve over a period of several years in the wake of the fire. Rachel would love to map the pattern and distribution of smoke and ash from the burn. Ha and Riley both have interest in looking at the impact of the fire on non-human persons, be that through a successional study or exploring how invasive species move into burn scars. I think we all have a desire to delve deeper into the human experience of wildfire and how it was felt more qualitatively by residents of the area. We are very grateful for all of our data sources and references we used in this project to create this quite extensive research prep. And with that, we would just like to say a special thanks to Dr. Elsa Kohler and Dr. Nathan Corderer for all of their guidance, as well as our wonderful leaders, Dr. Brady and Dr. Parr. We would open it now to any questions that anyone might have.
Round of applause for Metro State. Great job pulling all that together, you guys, and telling a really unique, interesting, locally relevant story, especially with all the fires that are happening now in the area. Anybody have a question that they want to put their microphone on for, or put in the chat for MSU? It was epic. One question I have for you was, like, you talked a little bit about, data availability. What were some of, like, you think the biggest challenges with respect to finding all the data?
I think Paul might have some interesting things to say there.
Some of the RAVG program by the USGS, they do have a lot of data on fire and vegetative data after fire, but the hardest thing to find was they were able to go into the site and record specific like vegetation and categorize them into groups, and we have data on what was lost, but not having data data on what specific vegetation grew back was kind of hard to do like a before and after analysis of the fire event.
Yeah, I think in addition to that, in sort of developing, like creating our data sets, like in terms of water quality and water monitoring, a lot of the times, a lot of these samples are taken maybe once every 6 months, and they don't really tell a complete story of how concentrations in water can change over time. And so finding like links between like ionic concentrations in water and precipitation events is really challenging because you just don't have the data to correspond to some of the other elements, because some of that testing is extremely expensive. And that was one of the biggest issues that I ran into in some of my research.
I noticed there's one question in there from Shannon about, do you think this same project could be done on tribal lands, or do you think data sovereignty would become an issue? Anybody want to speak to that?
I can. I know at one point in our initial search of what we wanted to study, we were looking for a fire on tribal lands to look at. And when we were trying to collect data, we were really running into the problem of having a hard time finding data available that was especially open access or had good frequency with it. So we were able to find a different fire kind of closer to within Colorado. But I think it would be really cool to see if we could scrounge up some data to be able to implement this on some tribal lands in the future.
Great question, Shannon, and thank you, Rachel, for your response there. I wanted to add a couple things. I know we're getting, I don't want to go too over time with folks. I know that OLC's got to go yet too, and they may go a little bit over. I wanted to pick on Megan real quick. Megan is one of our advanced interns from Metro State, and she's been working on a kind of a GitHub page for this project. And we don't have a lot of time to go through this right now, Megan, but I wondered if you would be interested or able to put a link to that page that you've been working on in the chat so that folks are able to go back and look at things that they might have missed or see where that lives.
Yeah, for sure. I'm putting it in right now. Yeah. There you go. And this is a project we did on Navajo Nation in 2023. So it was really
Perfect.
cool. Yeah,
Yep.
really fun.
Yeah, so this is I may have misspoke a little bit there. This is a project that MSU was working on from last summer, and Megan came back and created a page for that. And if we have time and resources, we may create a page for the one that we just heard about too, but wanted to say thanks to Megan for that. One other kind of announcement comment I wanted to make about MSU. You know, none of this happens without the faculty support and mentoring that goes on in these projects. Dr. David Parr has been our mentor at Metro State going back to 2020 when we were still the Earth Data Science Corps and still kind of getting things figured out. I think he had 1 year off to do sabbatical or something, but he's been here basically since the start. And so I do want to recognize Dr. Parr. He's going to be leaving us this summer to go off to larger pastures, I guess, over at North Carolina, where he's going to be taking on a new role teaching a spatial analytics course at UNC. And so I just want to recognize Dr. Parr for all of the work that you've done to help lead Metro State, I guess for the last 4 of the last 5 years, with help from Dr. Sylvia Brady as well. But just want to say thanks, David. David, you want to say anything before we jump to the last set of talks?
Yeah, this is my favorite day of the year. I love seeing all the projects and presentations from all the groups, and they're so meaningful. I show them to my students. We come back to them year after year, and I just got a email from one of my students from the first year asking for a letter of recommendation. So I love being able to keep those connections going on from year to year. But none of this happens without the support from CU, and particularly the support of Nate and Elsa. And I think they deserve so much applause and commendation for all their hard work, making this run year after year, making it smooth. I know all the groups work so hard, and then they get, you know, it's like 2 weeks out, they have no idea what they're doing, and then they get to the finish line and it's magic. So, and that happens because of Nate and Elsa and everybody at CU who's supporting them. So big thanks to them for everything that they've done. And I really enjoyed being part of it. Thank you all. Good luck, and don't hesitate to reach out anytime.
Oh, David, thank you so much for the kind words. None of this happens without NSF's help either, and so I want to recognize them as well. But yeah, I don't look at this as goodbye, but as a we'll see you soon, David. And so keep us updated on what you're working on. And I wanted to get that in before we go to the next talk. And so again, congratulations to MSU for a job well done, pulling together a lot of unique heterogeneous data and pulling it together to tell a great story.